Welcome again to this webinar on steel and composite design in SCIA Engineer 19. Sorry about the wrong slide here. SCIA Engineer 19 it should be. I will start with a few instructions about the webinars for you. So normally you cannot ask questions via the audio during the presentation, but you can ask questions via the questions pane, which you can find on the GoToWebinar app. I think it's below the attendees list, or maybe you just see the staff list. And also, after the webinar, the recording will be placed on our YouTube channel, so you can review some of the topics again or send it to your colleagues. So I have two important topics today: steel and composite design. I will first do the steel part, and then I will switch to the composite topics. So related to steel structure in version 19, we have SLS extensions. So inside the old relative deflection checks, we have improved significantly the serviceability limit state checks. We also updated the plastic hinges functionality. We have a brand new Swiss code according to the SCIA norm 263 and a usability improvement in the buckling settings. So first I will go in a nutshell with the three big improvements. I will show you live, and then we will review it again in a presentation so that it all sits in your heads after the webinar. So in a nutshell, what's new in SLS, in the SLS check for steel? So on one hand, now we support a check on variable load deflections. So in the past, we only checked the total deflection, and now we are able to, at the same time, check the total load and the variable load. We allow users to input camber on the beams. And so if we look at the standard image from the Eurocode, in the past, we only used to check the deflection per beam or per span. And today we are also able to split the deflection coming from dead load and live load and check the live load part as well against its dedicated limits. We also let users define camber. Another improvement is that now the check correctly supports cantilevers. So if we look at the same image and we try to extrapolate this to cantilevers, so here are the two beams. Let's assume that they have to have the same deflection, delta max or W max, doesn't matter. If they would have the same deflection, if we would like them to have the same curvature, that would mean that this beam will have to be 2 times longer. So what does that mean for the check? Actually, if we look at the curvature, we can say that in fact the length small l of the cantilever should be 2 times smaller than the length of this beam supported on 2 sides. And if we would write the check in this form, so the W max or the deflection should be L smaller than L divided by a certain limit value, then it means that we can write that off as small l divided by 100 due to the differences in these two spans, which means that the check is more economical. So this is now automatically handled in the SLS steel code check. Another thing that you should expect is a better speed, so around 4 times improvement in comparison to version 18.1, and also improved inputs. We heard from many clients that the previous way the inputs were defined, so these are the limit for the relative deflections, were quite difficult to work with. So how it worked was we had different beam types, actually the structural model types, and you were able to define limits for columns and for beams. But this didn't work in many cases, so we simplified that, and I will show you in more details how it works. But now we have a more simple approach, which also allows for customization. Now about the Swiss code, just one slide. What we did is we rewrote the previous implementation so that it runs in the 64-bit version of SCIA Engineer, and so the check is now available in the default or previously called V17 post-processing environment. The output is quite nice, the same as for the Eurocode, with all formulas with references. We also made the link to table results, and it's possible to, for example, show different components on the structure. We have error warning nodes in the 3D scene, which is the case for most of the new checks in SCIA Engineer. And we also extended the calculation of M critical so that it supports more, let's say, more cross sections, more load scenarios. And then also we have a brand new settings dialog. And a last improvement here, which I will show now in SCIA Engineer, is a way to preserve your buckling settings as you are modeling and changing the model. So let's start with SLS. So I have here this steel frame building, let's say not the most complicated, but relatively standard kind of hull with trusses. And I would like to check its deflections. So first I will talk about what you can find in the results service and explain a little bit the SCIA logic. So let's say that I would like to check the deflections on this lower chord of the truss. So normally I can use the 3D displacements, as of course remains available, and also under the beams service I can find 1D deformations. So let's say I would like to see the deformations of these of all beams that have these cross sections. In fact, these are these beams. I would like to use either a combination, so the characteristic SLS linear combination, or I would like to, I will also show you after that it also works in the nonlinear case. So then I would like to see the deformation. So I see something which I expect. Here I will use activity just to make it a little bit more clear. So these are the deformations of these beams. And so in a normal case, so here we have some column shortening, we would like to exclude this part from the check when we do the check on the relative deflections. So the relative deflections are also available in the service results. But what is the difference here? So let me just right now click on update, and what I will see is that the relative deflections are not what I expect. And I will show you the reason why. So this is, let's call it an existing functionality that it's important to understand before we run the SLS checks. Normally, the system length settings determine the spans that we use in the buckling checks and also in the SLS checks. So I have already used some system length settings, or buckling settings we often call them. I've applied them to these beams. So if I would like to have a look what is defined here, I will get a more or less an explanation of why I see these results. So here in the system length settings, normally people use it to define their buckling span. So buckling around Y axis, buckling around Z axis. And here we also see the deflection spans. So by default, these deflection spans are set to correspond to the buckling spans. But in this case, it works well for many types of beams. But in this case, I should go and define my separate spans for the deflection checks if I would like to check the deflection of the whole chord from here to here. How I do that? I can, via the graphical, let's say, window, turn off the supports, or I can simply go via the table, which I find more convenient option. So I can just go and I can deactivate these supports. It's a little bit of manual work here. But now I can see that for this direction, I would be checking the beam as if it is supported on these two locations. And also for this span, I would disable these supports. So now I have, for the buckling case, I can use these verticals to support my frame, but in the case of the deflection, I have separate settings. So I can just press save. Normally such actions shouldn't delete my results, but if you are working with nonlinear combinations and you're also adapting something like imperfections and so on, it's very useful to use the result locking. Then you know that your results will not be deleted as you are editing your settings. So here there is a button, result locking. Just in case that I don't misclick on something, I will activate it. So now I can go back to the deformations and I can plot again the relative deformation. And this is what I have. I can also maybe disable this this filter here, and these are my deformations on all of the active beams. Here I have smaller deformations because of the columns. So if you are this far into setting up your model where you've defined correctly your spans, you are more than halfway in doing your SLS checks. Let's say this will be your most difficult, let's say, action. So then let's move on to the steel service, where we will find the new SLS checks, which replace the old relative deformation service. So here I can, maybe I'll disable this filter. So I can check for the, let's say, run the check for a serviceability combination, the characteristic one. And here I have the check variables. I can work either in the two directions together, or I can separately look into the Z deformation and Y deformation. It's just a question of choice, so I prefer to do that separately. And here it's possible to again show the deformation. So what I showed you in the result service is also available here. Now what is new is the possibility to see the variable part of the deflection. So if I update, you will see that SCIA derives what portion of that deformation was coming from the variable load alone. And it also does that in case you work with nonlinear combinations. So if you go here to nonlinear combinations, you will see that I've defined, let's say around 8 nonlinear combinations of type serviceability. And then I have placed these in a class where all of them are run. And so I can go and run the SLS checks for the nonlinear combinations. And you will see that in this case, SCIA again derives the variable part of the deflection. So now we have the correct deflections. It's also possible to show the limits against which we will be checking these deflections. So these are the limits for the total load and for the variable load. Where are these limits defined? So if I go to the steel setup, there is a group SLS deflection checks, and you will see that the let's say layout has changed quite significantly. What we now define are 4 limit values. So for in-plane deflection, for the deflection Z, we have a limit for the total loads and we have a limit for the variable loads, and also out-of-plane deflection. So you, I think this structure is quite, let's say, stiff, so it doesn't have deflection problems. I will just adapt these limits just to show you that the check is responding to that. So if I go back to the SLS check and I run the check overall, I have the value of the check. So this is the, let's say at the same time, total and variable deflection. This is the total deflection and this is the variable deflection. So the same, everything you see on the screen is available in the table results. So let's maybe clean out the old tabs. So what we have here is the total deflection, the limit on the total deflection, and the check, and the same thing for the variable deflection, possibly also camber, and then the final value of the check. Now what happens if I would like to not change this, because this is affecting the whole structure? So I will just restore that to default. What if I have to specify separate limits for certain members? that I can do in the same way that I defined the spans. So if I go back to my buckling settings, under the deflection menu, I will find the possibility to override the limits. I think I will refresh here. From setup, these are the values that are being applied, and then I can override them. So here I can put something more drastic just for the purpose of demonstration. And I can also here define camber, but we will leave that for later. Here I can also change the limits just to test what happens. So I go now to the SLS check and I run the check, and I think, yeah, you see that now the checks are showing different results. So this is how we define limits. So limits for the whole structure and limits for a group of members. Now the next thing I would like to show you is how to define camber. So again, I go back to my buckling settings. Of course, I can define that on the level of the whole structure, but it will not make much sense. So if I would like to input a camber, I just use the possibility here, absolute or relative values. And I can say I would like to have 20 millimeters camber. Now, in which direction am I applying this camber? It's always useful to activate the local axis here so that we know. In this case, it's actually the z-axis is downwards, so it means that I'm applying the camber downwards. So I will change that to -20. And now just to verify whether everything is correctly applied, I can go and I can, the camber value, I can show it on screen. And so immediately I see that for some of the beams, I have the correct value. But in this case, I have LCS rotation. So these beams have a different section and their local axis is rotated. How to deal with that? One way is to simply copy that buckling setting. And then directly in this window, you are able to edit a lot of these. So for example, the limits, the camber. And then you can have a specialized buckling system, which copies all of the, let's say, parameters that were already defined. And here for these two members, you can define the following buckling system. So if I again show the camber, I see that it is correctly defined. So I can run the check in the Z direction, and then in the table results, I can see that the camber value of 20 was applied on all of the, let's say, members. This is just showing the value of camber at a certain section along the beam. So that's more or less what the SLS check does. So what we do with the camber, this is just, let's say, a member data value. It doesn't affect your model. It doesn't add additional bending moments. It's just used to verify the deflections. And also, you are able to plot the deflections together with the camber in the following way. Here, the camber is already taken into account, and you can see that for these beams, it's actually mostly the camber that is, because the deformations were really small. Now, I have another model which was, let's say, I made after discussions with some clients at the user meetings who said that they use other values of camber, not as prescribed in the Eurocodes. They use, for example, triangular camber. And they said that there is no way to define this in SCIA Engineer. So I made this model, which I called Polylines, just to let you know that SCIA Engineer has quite a lot of possibilities to model members as polylines. So if you have a look at these members, what I've done, so I just, to keep my results, I maybe just use the result looking. What I will do is, for example, if I select these two members, which I've modeled with two beams, I can go to modify, and then I go to polyline edit. And then I can use the function join curves into polylines. And in this way, I obtained such beams, or I can just model them to start with polylines. And if you have a look at the system line settings, what I've done is, so for the YY direction, I assume that this, let's say, chord is supported by these verticals and diagonals, but for the deflection, I am able to disable these supports. So now deflection is always evaluated between these 2 points. And the same also for buckling. We often get, let's say, comments from users who say, well, for buckling, I have, let's say, this triangular shape. I don't know how to take into account the correct buckling length. Well, this is the way to do it. You can use polylines in order to do that. So if I now go to the steel menu and I go to the SLS check, so here I use a serviceability combination, and here I can show the deflection. I think there may have been a problem with the saving of results. Yeah, I think I saw that there was a problem earlier today, but I thought it's because of the polylines, but no. So I will recalculate this model, and then I will rerun. And what you see now is that these points are assumed to be supported, and the deflections or relative deformation is calculated on these beams. That's related to polylines. And another thing that I also want to show that is possible with the new SLS check. Let's say we want to check the sway of the columns if we have something like a portal frame. This is possible in the current framework, and the way you can do that is, for example, again, defining a buckling system. So for these columns, what I can do is, for the, in this case, it's deflection Z, the Z axis of these columns, I can, let's say, disable this support. And here for the limit, I will put a value of 300, and I will later explain what I'm trying to achieve here. I think I clicked on the wrong place. Yes, should have been here. Yeah. So when I define these settings in this way, I can go to the check and I can run it for the columns, and I would like to see the deflection. So now I'm able to evaluate the sway of these columns, and this would be useful if I would like to check how much this building is deforming in a sideways motion. Why I used 300 for the limit. Normally in some national annex the value of 150 is given, but as I explained the story with the cantilevers, here if we activate the nodes, so just let me find the error warnings and nodes. I would like to see the nodes of these checks. So here it says the deflection limits have been multiplied by 2 because this is a cantilever span. So it still remains a little bit of a workaround, but it is possible to check sways. Just keep in mind that because this is considered as a cantilever, your limits will be adapted. I think this is more or less everything I had to show for the SLS checks. And then I would like to switch to the SCIA code. I just use this same model to and switched it to the Swiss code environment to show the main, let's say, nice things about the Swiss code. So I've calculated the model. I'm going to the steel code check. Swiss clients will find a brand new settings dialog, more settings than in the previous implementation because of a few extensions that we've done. A quick note, the SLS checks are also available in the Swiss code environment in identical way as in the Eurocode. The ULS checks, so if we would use the ULS combinations and we would run the check for the beams. So a few nice things. We have the result legend, which we can switch on and off. Also the error warning nodes. The table results are available. And also a few nice improvements, for example, in the summary output. we've added a few additional, let's say, details. So the internal forces have been added, and also the buckling parameters. So directly from here, I can verify the buckling lengths that are used for this polyline member. So flexural buckling, I can see that more or less the system length used was around 5 meters, and here for out of plane buckling, a length of 15 meters has been used, which is more or less the length of the member. Another nice thing is the detailed output. So it's possible to see that in a table form, but also in a formula form. So this usually gets controlled by the setting here. So formulas or tables or both. Switch to current and directly refresh. So you can verify how the calculations have been done. Also, the M-critical method, as I mentioned before, we have implemented a general, let's say, generic approach for the derivation of M-critical because the Swiss norm only supported the derivation for symmetrical sections which are loaded in their centroid. Another nice thing that is available, sorry, not here, in the Swiss code environment is the possibility to use the classification and effective section tool. So these were previously not available according to the Swiss norm. So now it's possible to say I want to see what the class of the section is if I load it with certain internal forces. I think this functionality became available in for the Eurocode in version 17, I think. So now it's possible to classify these as class 1. And another nice feature is the effective section, which we can directly derive in compression. Of course, this section has no reductions. And now I will show you the last thing I wanted to demonstrate, that's the buckling cache. So imagine now that we have inputted some buckling settings on our members. So I think I had it in the other model. Maybe it's better to use this. So I have assigned buckling settings to some of my members. And what the problem was in version 18.1 and before is if I would disconnect the members or edit the model in a certain way that the number of spans would change, then the buckling system gets invalidated and gets taken out of the member, which meant a lot of problems for having to define that again and again. So now I will demonstrate to you what solution we came up with. So here I will select all the members and I will disconnect. So, okay, 26 nodes have been disconnected. So as done previously, again, these buckling settings have been set to default. But what is the difference here is that in the cache, the buckling group is still stored. So if I would come to a moment where the settings are again applicable, I can again automatically reassign them on my members. So what happens normally is that as you model the member, and especially if you have some 2D members and load panels, and you would like to delete a node or you would like to move something around, you always get these messages that the geometry is not valid, so you can't adapt the model. And the solution for that, of course, is to disconnect all members, do your modifications, and then reconnect them. And so now the difference in version 19 is that if I run connect, I proceed with all entities, there is this option auto restore buckling group when reconnecting. So when this is on, I can reconnect, and here I receive a report. In this case, everything was correctly assigned to the members, but you will also, in case something is still in the cache and not reassigned, you will get a report here with the following buckling groups were not assigned to the members. And if we test again, we will see that the buckling settings are put back on the members. So I think this was everything I wanted to show live for steel. And so I would like to now just refresh with going over this PowerPoint presentation. So about SLS, what we saw is what is the difference between deformations and relative deformations, and how to set up our relative deformations correctly so that we can get the result that we would like to in order to run the checks. I showed you how to and where to find result locking so you don't accidentally delete your results, especially if you have nonlinear combinations. And especially if you're going to be dealing with settings which can model your can change your model and delete your results. The functionality is quite general. You can use it also when you are deleting members, adding members, etc. The next thing I showed is that the SLS check automatically derives the variable portion of the deflection so that it can check it against its specified limit. Also in the case that you're working with nonlinear combinations. Then I showed you limit deflections that you can show them on the structure. So these are the maximum deflections against what we are checking against. You can define them for all members, so in the steel setup, or you can define them per buckling group, which means per span. Also, intermezzo here is in the settings of system length and buckling group. So this is the main dialog. You are able to modify many settings at the same time. So you don't really need to open the specified buckling group and change it there. You can work from this window. So this is just an example of how you can change the limits. Polylines, I explained how you can join members into polylines so that you can correctly take them into account for buckling and for deflections. And also how it makes it possible to work with that kind of, let's say, camber shapes or just more complicated geometries. Here in the SLS check, I showed you that it also takes into account polylines. So this is a correct way to handle spans, but also, let's say, explicit input of a triangular camber. I showed you how to input and verify that the camber is in the right direction. And also about column sway, I explained to you that you can check that also via the available settings. So how to obtain the correct deflections and how to check them. Also here I've taken this from the French National Annex. So the check we are aiming at is checking this overall sway of the building. So height against the horizontal displacement. What still remains not possible with the current implementation is the check of, let's say, interstory drifts. And soon we are launching a steel, timber, and composite survey that we will send to all of our clients, and you are able to vote. This is one of the topics that is listed there as potential development. So if you think that this is something important that we should develop, you can vote for that. Something that is almost finished and will be available in 19.1. I just want to give you a sneak preview. That's the camber design. So how it works, if you set camber design and you run it for the whole structure, SCIA will ask you your production limitation. So what is your minimum camber? What is your maximum camber? And how should we round camber? Let's say to 5 millimeters means 5, 10, 15 millimeters. So let's say that you have failing SLS checks, then you can just run it with a camber design and SCIA, if possible within these limitations, will derive a value of camber per beam, which will fit you with all of the SLS requirements. So like this. And it's also possible to limit the camber to a % of dead load deflection. Some words about speed. So if you test it on a, let's say, standard building, what you can expect is that the SLS check is around 3 times faster than the ULS check, which is already quite a fast check. And also some preliminary measurements of the camber design. We see there that if you have complicated spans, then you may end up with, let's say, comparable values with the ULS check, but still faster than the old relative deflection. service. Then another topic, I will not show it live, I will just shortly mention it, plastic hinges. So plastic hinges, first of all, because it's not a very, let's say, popular feature in SCIA Engineer, not many clients use it, I want to explain where is it used. So here you see a comparison of two different frames calculated in SCIA Engineer, once in a linear calculation and once the same frame but with nonlinear analysis with plastic hinges without geometrical imperfections and geometrical nonlinearity, just plastic hinges. So what happens is in this model, we see that the unity check is fulfilled. That's the section check actually, and in this case not. So how does this work? As soon as the capacity in certain section, in this case it's this section, but somewhere on the structure, the capacity of the steel cross section for moment, but also reduced for normal force and shear would reach 1, then a plastic hinge will form, which means that this moment here will remain limited to 244 kilonewton meters. And then the diagram in this case will shift down. So this moment will grow as the load increases and this moment will grow, but this moment will remain fixed. This allows us to use more of the capacity of the beam because then we will have, let's say, a more uniform utilization. I think I've overlapped them here. It's not very clear, but I think here it's around 0.8 and here it's 0.4. So the whole idea of using plastic hinges is for economical design. And what we've done there is, on one hand, we have migrated the functionality to the 64-bit version, but we've also rewritten it according to Eurocode 3 as it was previously written according to the pre-norm ENV. And it did not support any national annexes. So now, depending on your national annex and your safety coefficients, then you will get the proper calculation of bending moment resistance. In the past, we had a hard-coded value of 1.1 as a safety factor. But in this case, for most countries, the functionality will be more economical. So here I have, for this frame with a variable cross sections, in version 18.1, it tells me that the maximum load that this frame can carry is 24 kilonewton meters, and in version 19 it's 26 kilonewton meters. That's about plastic hinges. Now, to revise the Swiss code, what did we see? We saw that all the check tools available for new checks are also now available. We are able to plot various result components. So for example, we can plot normal force, bending moment, shear force, LTB. We can also customize these tables. In the table results, the summary output has been extended with buckling parameters and internal forces. The detailed output has been extended. And also here we have decision tables added. So this is an explanation of why we use a certain formula to perform the combined check. Some words about the M critical. So we are using the general approach according to ECCS 119. And the reason was because in the Swiss norm, we had too many limitations. And so the check was quite limited. So it was the load had to be applied in the center of gravity of the section. The section had to be doubly symmetric I section, and also the load had to be there was no load allowed in between LTB restraints. It had to be linear, so every portion between LTB restraints had to be loaded with end moments. And because of that, because also the Swiss norm allows the use of the methods used in the Eurocode, we decided to take a more general approach. Also for the Swiss code, we have classification tool, let's say, also used inside the check, but also as a window that you can use to do some manual calculations or test some initial designs, and an effective section tool. Keep in mind that the Swiss norm only supports local buckling in the calculation of the effective shape. They don't have the methods in part 1.3 in the Eurocode. So if you would like to do cold form steel sections, it's still advisable to calculate these according to the Eurocode. Here is an example of a C-section. There is no reduction at the stiffeners for distortional buckling. And the buckling system cache. So there are many ways in which in the past was possible to lose your buckling settings, whether you are moving members around, you are splitting them, or you are adding hinges. Now it's possible to, in all cases, cache your buckling settings automatically, and as soon as they become valid again, you can restore them back on the model. Now I will say a few words about composite floors. So version 19 is focused on, let's say, finishing the functionality so that it, let's say, polishes all of the previously done improvements in that module. So I will quickly mention to you what were the extensions in version 18.1. In 18.1, we added openings according to the Steel Construction Institute publication P355, which lets us, let's say, check any combination on the beam of rectangular, circular, and elongated openings. And it also tells us how to check the web posts in between the openings. What we also added in 18.1, we support the SCI publication P405, which lets us reduce the minimum connection between the beams and the slab in order to obtain a more economical design. And also we improve the frequency checks by making them more accurate and also allowing the user to define more parameters. Now, version 19, the first thing we had to look at was the speed, because after we added the opening checks, we saw that the speed for beams with many openings was not satisfactory. So on average, we can say that for a beam with a few web openings, we can expect around 5 times faster checks. But that's also, the more openings you have, the better the improvement. We worked on the report. We did many improvements in the summary output. What we did is we significantly shortened it, but we added more things that were missing in the past. And we also added all references in the detailed output, because it was hard to follow from which standard the formulas are coming from. And we also revised all error warnings and notes. And probably the biggest improvements that we did were in the auto design. On one hand, we now change the logic of the auto design so that we look at the sheeting geometry at first in order to obtain the optimum layout of the studs. So let's say every trough or every second trough. And based on that, we then find the optimum cross section, which also helped us in achieving a more, let's say, efficient auto design. Just to show you a comparison of the speed, so this model that was used for testing during the development, in version 18.1, it was not possible to, on my computer, to run this at once for all beams. After 15 minutes, still there was no result, and I think that it was not going to eventually give any results due to running out of memory. In version 19, we reduced that to 33 seconds. And also, if we just would run the check on these 10 beams, in version 18.1, it was around 50 seconds, and in 19, we reduced that to 8 seconds. I will go back to SCIA Engineer, and I will open a composite model with openings. And on that model, I think I will be able to show you all of the improvements from version 19. So I have this floor that I've actually optimized for the state of it without the openings. And then on top of that, I have added web openings. I've used the general, the general 1D opening option in the structure service under 1D members. There is the openings. And there we have 3 types of openings, which this one was specifically added recently for the composite checks. So you can input a rectangular, a circular, or elongated shape, and this will be checked in the composite checks. This one is not supported. This is a very specific functionality. For example, if you want to have an opening with an I section form or something like this, or any kind of form, you can use this, but this is not explained in the SCIA publication. So I will go to the composite service, and then I will run the checks on the beams. So you will still notice some slowdown on the beams which have openings, and this is because of the high number of finite elements, because in SCIA, when we model openings, then this will also be taken into account in the calculation of deformations, including shear deformation. And because of that, there are many finite elements here on these parts. So you can see for some checks it goes really fast, and for some of them it's relatively slow. So more or less you can see that all the beams were optimized previously, and then after adding the openings, they do not fulfill anymore. If we go to table results, I can directly show you, maybe select one of the beams, for example this one, and I can show you how the standard output looks today for a beam without openings. So you will find the input parameters are just half a page now, and then what is new is also these fields here of, for example, vertical shear, what is the applied shear, and what is the allowable shear. So all the different checks in the different stages are listed, the detailing conditions, and also the shear connection, for example, comparison, and then the studs, etc. Here we can see that we needed, let's say, 27 studs, and we have 27 ribs to place these. That's more or less the standard output, but I will now try to launch the optimization for these beams. I see here problems. So, okay, practical geometric limits are not fulfilled. Here I can see some other problems. So what I can do now is I will just run the optimization, but let's just run it for the selected beams. And so SCIA, very often in the past, when we had very complicated opening layouts, SCIA was not able to find a solution. That was version 18.1 for the auto design, and in this case, still some solution is proposed. So I will go for it, and maybe I will just select these beams, and then I will rerun the check, and then I will also show you the output in the case of the opening checks. So still we will have to wait a little bit because of these were, let's say, the most heavy beams, but it's still, let's say, acceptable speed, at least in my opinion. If you don't agree, you can argue with me. So now I will show you an output, how it looks in the case of openings on the beams. So here below the beam and slab properties, we will see the properties of the openings, where they are located, what's their geometry, whether there is reinforcement, the properties of the web posts, and also here we see the practical geometric limits. So this is a check which is given in the SCI norm for, let's say, whether your beams are complying with their set of beams which they have tested, but they still allow for beams outside of that range to be designed using engineering judgment, as long as all of the checks are fulfilled. You can also read it yourself, that paragraph, and decide whether you would like to design beams that do not fulfill these or not. But we don't at the moment consider this in the optimization. We just notify the user. I think if these are not okay, you will also see a warning here. The practical geometric limits have not been taken into account. They have not been met for all openings. Please check the output for more information. But for the other checks, so for example, the openings in construction stage and the openings in final stage, all the checks are fulfilled. Also, what we've added here is more information on the openings. Also, how many studs have been used. So, for example, this is opening 10.1. 10.1 is this opening, and it's listing us that it uses one opening from the opening to zero moment, and one stud from opening to zero moment, and one stud on top of the opening. So we can verify whether that's correct. So from here to here, yeah, we have one stud and then one stud on top of the opening. So we made it as much as possible that it's possible that the user can verify the results. Then I can also show you maybe for this beam. This is a little bit more difficult, computationally heavy beam. It's a cellular beam, rather randomly modeled by me. Maybe it's not exactly the correct geometry. So what we see here is a long list of openings, circles on the beam, web posts that have all been checked. And here it says these openings are too close to each other, and also the distance to the end of the member on the end is too little. So the SCI would prescribe that I will put them a little bit further apart, and that this end post will be a little bit bigger. But for the rest, all the other opening checks are fulfilled. So I think that's more or less everything I had, but I will go through my presentation just to remember if I forgot something. So the summary output has been made, let's say 30% more compact. So here, this was just the input part, which was significantly shortened. There's more useful information, and all the irrelevant details were taken out. Also, we managed to optimally use space by adding some important information about the design. And also the stud layout now is more realistic. We also draw the openings, and that's more or less it. We added the camber value, some analysis settings that are used, and more data on the opening checks. Now, the references in the detailed output in the composite checks, these are quite important because these checks use quite many different documents, and it was really hard to follow where is which formula coming from, especially because the name of the norm was not used, just the formula, and it was very confusing. So in version 19, this is significantly improved. Version 18.1 was very difficult with warnings, so most of them were condition given by is not fulfilled. So now we've rephrased them, and we have, for example, the shear connectors must extend above the top of the steel deck by a length more than twice their diameter. So now I know what I have to edit in my model in order to not get that warning. Examples of beams that were not possible to auto-design in version 18.1, now without a problem, SCIA is able to find a solution. And because this is a lot of information for people who haven't used the composite module, if you're interested, there exists a tutorial where the modeling, the analysis, the design, and also nonlinear analysis, stability analysis, and certain details of these functionalities are explained. So if you are interested, you can contact me, or you can contact support, and you can obtain this tutorial. So this is all the information I have for you today, and I can now start answering questions. If you, yeah, I will go. I see there is a list. So somebody is asking deflection, which happens deflection due to creep. Well, because this was a steel functionality, we didn't include any checks on long-term deflection because it's not relevant to steel beams. Such a check is included in the timber functionality, and I believe also in the concrete functionality. Then let me see some other questions. There is a question about the stress limitation in the composite beams. At this moment, we don't do a stress limitation check because the Eurocode says that it can be ignored. But if you would like, we can start a discussion on that, whether there may be cases in which it would be necessary, and we are of course willing to add that check. So far, I can also send you the reference where it's mentioned that such a check does not need to be performed on composite beams. Then the next question was sway system according to buckling analysis. This I... Geometrical nonlinearity. If you use geometrical nonlinearity, you have to define your initial imperfection manually. Another question: are these features available in SCIA Engineer student version? Yes, certainly. So if you have any more questions, you can... Are these slides shared somewhere? I think that the slides will be sent to the attendees by our marketing team after the presentation. In case this is not the case, you can indicate to me, and I can, if you have an email address that I can send to, I can send you the slides. There is a question about the steel decking library. Do we use special sheets? Yes, but you can also define your own. If you go to libraries and then you go to composite, there is profiled steel sheeting. And then here, usually libraries of manufacturer things are in SCIA available on the blue folder. So here you will find ComFloor sheets. Then here are the ArcelorMittal sheets, which are available actually since version 19. So this is new. Then we have some German manufacturer products. We also have Kingspan, and I think these are American products. We are always willing to extend that library. If you see something there which is missing, we can always add it, so you can indicate to support or send me an email. Composite columns are also possible to design in SCIA Engineer. Since I think at least 7 years ago, there is a module for that. So how it works is more or less, I won't go into the details, but you can go to the composed sections, and these are the possible composite column layouts, and there you can input reinforcement in the way that you do that in the concrete service. So what you will have to do is you will have to activate the composite column functionality. It's this one, and then you will get another composite service, and there you can define your composite columns. The drawback is that this one is not compatible with the composite beams, so because of conflict of data, so when you activate this old module, then you will not be able to access the composite checks for beams. Somebody is asking about a webinar of cold form steel sections. We are actually working on extending and improving the cold form steel functionality at the moment for version 20. So we are planning to then release. So in version 19.1, we hope to have some improvements, some additional form codes. And then in version 20 to have a brand new cold form check, and then we can add a webinar for this. Then a question, how can you input imperfections? Normally you can input these if you add nonlinear combinations, and you would create your combination. There is possible to define your bow imperfections or your global imperfections. There are quite many possibilities there. You can define it manually, you can use a load case to define the imperfections, and so on. So for example, if you use the Eurocode formulas, you can define them in the buckling settings, or here you can specify your value of imperfections. I think that's more or less all the questions that I see. So I suggest to end this webinar. Thank you all for joining. And if there would, I will go through the questions again. And if there would be any additional ones, I can send you additional information. I see a new question about Alplan link. I think it would be nice to send the question separately, as it's let's say along another topic of discussion, BIM and Oplan, but we certainly interact with Oplan. So send us all your questions. I show you again my email address and any suggestions for improvements. Thank you very much, and yeah, have a nice day.